I would say today's, at least the beginning of it, is going to be really pretty straightforward, which is nice. And we're going to find what's called the average value of a function. So let me show you what the problem looks like. Suppose we have a function, starts at A, finishes up here at B, and the function's called, say, y equals f of x. Then at any given point between A and B, isn't the height of the function going to be different? You know, here's just random places, right? Well, the average value of a function is the average height of a function, if you like it that way, right? The average y value. Now, can you see it might start as low as here, but it climbs up, and then it goes down a bit, and then it climbs up a bit. So there's a single number that represents the average. One way of doing it, couldn't you take like 100 different values of x between A and B, find out the value of the function at those 100 points, right? And then just add them all up and divide by 100. Now, that wouldn't quite be perfect, but that'd be an estimate. But no, how do we do it? Well, first let's get you used to some notation. When you see that, it means average value of the function f of x. And here is your formula. It's 1 over b minus a, the integral from a to b, f of x dx. So the average value of a function is actually the area, right? All of this, the area under the curve, right? Divided by the distance from A to B. Kind of makes sense, you know? Area divided by, isn't width times height the area? Well, if that's the width, wouldn't the average height get you what you need? So it kind of makes sense to me that that's the formula. So what do you get? Well, your questions, many of your questions, will be straightforward. They'll give you a function, and they'll tell you where to start and where to finish, and they'll ask you to find the average value. So for example, suppose f of x is 3x squared plus 4, and the values of x go from -1 to 1. That's what that would be. Find the average value of the function. This is very similar to question 1. Well, here goes. It's 1 over b minus a, the integral from a to b of the function dx. In this case, it's 1, basically that's a and b. So it's 1 take away -1. And the integral is -1 to 1 of 3x squared plus 4 dx. Right, before I actually work this one through, is it possible, do you think it's okay if you get an average value that's 0? Could that happen? What do you think?
I think so.
Yeah. Can you imagine a sine curve up and down? Wouldn't the average be 0? Because we're doing a net area, right? We're not doing a physical area here, so that could be negative, couldn't it? Could be positive, could be 0. So it's okay to have an average value that is positive, negative, or 0, right? There's no restrictions. So if you get a negative number, you say, oh, okay, most of the curve is below the x-axis, that's why. This is a half. Power rule. Add 1 to the power, divide by new power. Evaluated at -1 and at 1. If you plug in 1, you get 1 plus 4. Take away if you plug in -1. It's a bit messier. -1 cubed plus 4 lots of -1. Okay, let's see what we get here. 1 plus 4 gets me 5. That's -1. That's -4, so that's -5. And so I get 10 over 2, I get 5. So the average value of this function from x equals -1 to 1 is 5. Does that seem, as a process, seem to be pretty obvious what you have to do? So what you're really going to do in this section, at least for the first part of it, is practice at finding integrals again. Just an application, right? A reason to do it. So let's make it harder. That one is basically a power rule, right? That's the method we used. How about this fella? Going to call the function g of t, and it's going to be 4t over the square root of 8 plus t squared. And t is going to go from 1 to 3. This is kind of like question 4. So the average value is this guy. Technically, if the variable is t and the function is called g, then you'll use g of t dt and you'll call it g of, right? 1 over 3 take away 1, the integral from 1 to 3 of this ugly guy. Okay, we got a problem of integration. I need to integrate this. It's definitely not a power rule, definitely not, some algebra I could do to make it look better. You agree it's a u sub? What would be a u sub to work with this fella?
8 plus t squared.
Yeah. So differentiate with respect to t, and you get 2t. Do the crossover, and then isolate the dt. Right. This fella is a half now. It's going to be the integral of 4t square root of u 1 over 2t du. Cancel out the 2's and the t's, and you've got 1/2 the integral of 2 over the square root of u du. It's looking much nicer. Anything you think I might be able to do in this integral just to make my life a little bit easier?
Bring the u up and make it to the -1/2 power.
I definitely agree on that. See this half that's here, it interacts with this 2, agreed? Right, this half on the outside, doesn't it interact with this 2 on the top? And when you put them together, what would they become? A half times 2. Right, 1. So, guess what? They came out quite nice. Now, don't expect everything to come out as nice as this. There might be a 7 left over somewhere, some weird fraction, whatever. You live with whatever you get. But if it comes out nice, use it. Now, this is a power rule, agreed? So you add 1 to the power, and then you divide by the new power. I think we've done enough u subs, hopefully we've done enough u subs for you to realize what the next step, I've put over here, what the next step should look like. What should I do next? What should I write down next?
Replace the u with 8 plus t squared.
I totally agree. I will do that. What about the half? What will I do with that? This half power.
Square root of the u.
Agreed? Square root of u, and then someone said, let's replace the u with 8 plus t squared. Now, at this point, can't I then introduce the limits of integration? So you notice how I leave these blank so I don't get into the nasty habit of thinking I can just plug 2 square root u and make it u1 and u3. It doesn't work that way. If you wanted to do that, there are ways to do it, but not that way. Okay, so you plug in 3, you get 2 square root of 17. If you plug in 1, you get 2 square root of 9, which is 2 times 3, so you get take away 6. And there's your finish, your end result. We only want exact values here. That's totally okay, right? That's the way the answer has to be written. I guess I could put the line in because I said it out loud. 8 plus 3 squared is 8 plus 9. Take away the square of 8 plus 1 squared, right? And that's the 17, and that's 9. And 9 gets you 3, and 2 times 3 gets you 6. You happy about where it came from? Right, that's that question finished. Right, find the average value of a function. The reason I picked this one is because I thought it was a nice u-sub, right? Just to, get our brains thinking. See if I can find something weirder or different. That didn't take long. Tell you what I'm going to do instead, because there's just so many. I won't have time to do every single possible, thing that could happen. So we can talk through some of them. The one we're going to look at is, here we go. They are nice and big, maybe even bigger, right? There. Hopefully if you've got a small screen, you can still see what I'm talking about. We're going to find the average value, and we're not going, and that's the question, but all I want to do is look at how you would integrate the given function. Okay, that's question 7. What method would I use to integrate question 7?
Finding the u.
Okay, who's the u sub in question 7?
Sine t.
Agreed. Right. What about question 8? What method am I going to use here?
Same method.
Correct. And the u sub?
X cubed plus 33.
Nailed it. Agreed. Now, right now, there's power rules, right? And that does include things like square root of x and all that kind of thing, right? That's one group of questions, and they're pretty common. Aren't there another big chunk of questions that are all u subs? The thing about u sub questions is, don't they look quite different from each other? An x cubed plus 4x kind of looks like every other x cubed plus 4x, right? But don't u sub questions just look weird and different and all sorts of combinations? So right now, if you see a weird or different, you should be thinking u subs, right now. Later on, we're going to show you another technique called integration by parts. But for right now, they're the only two guys in town, right? So when I look at question 9, I say, God, that's weird. And then I think to myself, is it a trig identity that I'm looking at? Just in case it is, because sometimes there might be. And nope. So it must be a u sub. So who's the u sub in question 9?
Cosine x.
Yes, not the sine, but the cosine. Can there's a good u sub and there's a bad u sub in this case. The good one, which is the cosine, works. The bad one, the sine, doesn't work well, at least. Log u on the top over u. Technically, I'm going to have to call it a w sub, right? Because u is being used up. So what is the w sub in question 10?
U.
Think again.
Oh, yeah, the natural log.
Yeah, natural log of u. You never get a u sub of just x, right? A u sub of x never does anything. It just changes the thing from one letter to the other, but the function at the end looks identical to the original. So there's no benefit. In this case here, wouldn't that guy just be a trig, you know, integral of a trig? And for this fella here, wouldn't you have to use, remember the linear shortcut method? So when you integrate, forget about the -5 for a minute. If you integrate sine of 2x, you get negative the cosine of 2x times a half. That's how that one would work. There's a nice polynomial, weird trig. Won't do anything about that. Okay, let's travel back. Okay, we've covered a few examples of techniques to use. What we guess I have time for is maybe one of these fellas. So where did I start? All right, I'll start here, I think. So we could do question 7, that looks like this. We can do question 8, which looks like this. We could do question 9, that looks like this. Or lastly, we could do question 10. Which one of those 4 do you want to see? Do you think, yeah, I'd like to see that one done? 7 to 10.
I can only speak for myself, but I would like
So, go for it.
just 9.
You don't like the looks of 9, or you want to see what 9 looks like, right?
Kind of want to see 9.
Yeah,
Yeah.
I was going to say the same thing.
As good as any. I can tell you right now, probably somebody wants every one of the 4 numbers, but if you don't speak out, you lose it, which brings me to something I'll be talking about after this. So we have a function, which is, in this case, 3/4 power of cosine with a sine, and we're going to do it from 0 to pi. Okay. And it's a standard find average value of a function. So they're not doing anything different. See what it looks like. Well, it's 1 over b minus a, which is pi take away 0. The integral from 0 to pi. And I'm going to rewrite this guy like that. Right, the 4th power of cosine is this guy. Now, we already talked about the technique, and the technique was it's a u sub, and we got the correct u sub, which is use cosine. Are we comfortable at this point what we've written down? You know where all these pi's and zeros come from, and a u sub is the way to go. Right, if you differentiate a cosine, and remember it's differentiate, what do you get?
Sine?
Negative sign.
Negative sign, right? We are differentiating. Do you know that sometimes you differentiate and sometimes you integrate? In u subs, that's exactly what you do, don't you? You differentiate first and then later on you're going to integrate. Now you do a crossover. And then you isolate the dx. So this guy becomes 1 over pi. The integral from 0 to pi, 3 u to the power of 4, so it's a little bit clearer why I got that. A kind of orphan sine x, a negative 1 over sine x, and a du. And exactly what we wanted, a little bit of cancelling. And now we're looking at the integral of negative 3 u to the 4 du. And add 1 to the power and divide by the new power. So we get that. I would bring out all these guys. And that just leaves me with a u to the 5, which I'm now going to turn into a cosine and evaluate it at 0 to pi. I have this guy, take away that guy, essentially. Okay, so this is the 5th power of cosine pi. The cosine of pi is negative 1. And -1 to the power of 5 is -1. The cosine of 0 is 1, so you're taking away 1. And so you're going to get -2 out of that. -2 times this gets you +6 over 5 pi. We got our answer. Are we okay with that question now? It's actually not as ugly as it might have looked, right? Could have came out worse than that.
So you were still able to cross out sine x even though it was a negative sine x?
Yeah, I left behind the negative, so it's still there. I only cancelled the signs. Right. So yes, you're allowed to do that. Yeah, you can cancel like with like. Positive and negatives don't stop you doing that. You just have to make sure that you take care of that in the process. Is the answer positive or negative when I'm finished? Any other questions? Are we good to move? Right. Change in tack. This is not anything to do with what we're doing, but it is important. So I want to show you. Once I get my act together. I want to speak a little bit about oh, come on, where are you? Wow. All I need to do is leave for 5 minutes and I end up with 20 emails. Where's the email I want to show you? Okay, zoom. Oh, shooting space. Can never, found it, yay. Okay. I'm always pleased with myself when I don't swear. I said shoot, S-H-O-O-T, for instance. Come on, you should be are you not proud of the fact how much self-control I've got? Right. I share a story because it's coming into my head now and it has to go out. As you may or may not know, I come from a very large family. I come from a family of 10 children. And my mum and dad decided, or didn't decide, whatever it is, to have a boy first, 6 girls, and then have me. So when I was growing up, I had 6 big sisters and my mum. An awful lot of girls in the family. I vaguely remember my brother getting married, so I think it was 5 or 6. So I never had a big brother. Right? Tons of big sisters, and they are cruel. They are. And I had 7 mothers because I could not get away with anything. So I think that's why I don't swear much. I think in my childhood, if I swore, I would just get into trouble because one of my sisters would tell on me. Right? And so that's one of the little things. I think I'm generally a nice person. That's also true. But to give you an example of what they did to me when I was really young, like a baby, they would dress me up in like it was a toy. And they would dress me up in little dresses and, you know, little baby things with frills and things on it. Because when you're a baby, you can get away with anything. And my hair was long, so they made it into little curls and ringlets, put little bows in my hair. I mean, they done some horrible things to me. They done all of that. And anyway, they had a pram. You know what a pram is? push thing, baby push thing, right? They were pushing me about in this pram and outside on a summer's day, and one of the neighbours came over and he was looking and says, "Oh, the new baby. Oh, it's pretty," and so on. That was fine. And then the next day, that person met my dad and says, "Oh, I just saw your new girl. She's beautiful." My dad said, "What new girl? It's a boy I've got." And my dad finally took an interest in the baby and saw what they'd done to me. So what happened to me is that I got my hair, like we call it a crew cut, you know, like there's almost no hair left. Off went the ringlets. My hair never got more than 1/4 of an inch. That was it. Nobody's going to call my boy a girl anymore, right? And that was that. And that continued. You know, when your dad's your boss, you get the hair size that they're going to get you, right? At least in my family. And I got to about 18, 17 or 18, and I finally, you know, did that rebellious thing. So I grew long hair because I wanted to. And I did it for about 2 years. My hair was like down to here. And then one day I figured out long hair is a pain in the butt. You have to shower with it. You have to dry the bloody thing. You have to comb it and look after it. And I thought, what the heck with it? So I got my hair cut back into short hair again. So I don't know why I shared that with you. I guess I'm homesick. But it just shows you what happens when you are brought up with lots of girls. You don't swear much. And they try and dress you up. So if any of you have got little brothers, will you remember that? Because little brothers turn into big brothers. And it's a surprise to me that I still like girls, but I do. So moving on. I forgot what I was talking about. Oh, have I switched over? I don't think I have yet. This is the thing. This is the real thing that I think is important. OC Foundation Scholarship. I want to make sure you all are aware of it. There is $300,000 free dollars out there. 300,000. A big chunk of change. Most of you need that kind of money, so I strongly advise that you apply for it. You should have got an email. If you've not, go looking for it. Just go onto the site and type in the foundation, FOUNDATION, and you will come across it. 300,000 for this coming year. OC is about 20% reduction in students in the last year because of COVID. So you now have a 20% better chance of getting the scholarship because there's 20% less people. I always tell my students, you can't win it unless you're in it. Apply for the darn thing. You don't know who else has applied. You've just as good a chance as anyone else to it. And they aren't all for 4.0 students, and they're not all for students who do not have a lot of money, right? There are all sorts of scholarships for very specific reasons. If you want to become an engineer, for instance, there's scholarships. That's all you need to do. Be taking classes that engineers take. Right? They don't care how old you are. They don't care how much money you do or don't make. They're interested in helping you along your career to become a scientist, anything in the mesh field. So look into those. There's a link here, and what they have now, which is so much easier, is that you can type in your general information once, and that gets you a lot of scholarship applications already set up. So you don't have to like fill in my name, my age, and all that stuff, my address 42 times to do 42 scholarships. You can enter it once, and that information is used in all of them. So have a good look at them. I get 10% of every scholarship that students get in unmarked bills, which Evan is going to describe to some of you who don't know what that is. Actually, I don't get any money, but I do want you to get money, right? So go for it. Any questions about that before we return back to what I get paid for, which is teaching math? Are we good? Have any of you seen this email as it came through yet? Right. Don't throw it away then, right? Go into your trash bin and bring it back out if you accidentally did that, because you know you get 40 emails a day and you can't do everything. Okay. At that point in time, I close this window off a minute. Okay. Where's the? I've got another question I'm trying to find here. Yeah. Down here. Yeah. Okay, here's it. This one is like question 17. I'm picking the weirder ones, the even weirder, I guess, than some. This fella. And I just realized you can't see a darn thing, can you? You were just going to let me rant on for 10 minutes and then maybe casually mention we can't see anything. Weren't you? Bezida, you were going to do that, weren't you?
No.
Good. Okay, so it is our standard find the average value of a function. Right. Agreed? No problem, sir. Anybody, any guess what the answer is going to be before I do this? Just a guess. Gut
0.
feeling. Yeah.
Yeah.
Yeah. Well, what? I agree with you. That's my gut feeling. That doesn't mean I'm right, but that's my gut feeling as well. What was your thinking behind why you think this is going to be 0?
Well, a sine wave just repeats itself, and we're going from negative pi to pi.
Yeah. That's what my thinking is. If you want to visualize a typical sine function, can you see the bit in the top is going to be exactly balanced by the bit in the bottom? Now, that's my gut feeling, but we got to do it just to be sure, right? You can't just write 0 and, you know, throw the coin in there. Hey, I picked heads and it was heads, right? You got to do the work for it. But at least we kind of have a feeling for what it's going to be. So it's going to be pi, right, that's B. Take away negative pi, which is what A is. The integral from negative pi to pi. Another reason I liked this question wasn't just because I thought the answer was 0, because I want you to see 0 can happen, right, as a possible average value. Is this AX here? Because it's a linear shortcut method. If you integrate the sine of 8x, right, the sine of 8x, you will get negative the cosine of 8x. And what else will you get? Because this is called the linear shortcut method. What else do you get because of that 8?
1/8.
You get 1/8, which I'm going to stick down there. Now, this is 1 over 2 pi. This is 1/4. This is the cosine of 8x. And we're going to evaluate it from negative pi to pi. I haven't started evaluating it because I want to see if we can take care of some bits. See this negative 1/4, wouldn't it be just less hassle if I could just pull it outside and join the others? And if you think about it, isn't all you need to do is multiply these together? And so what's that going to give me? It's going to give me a negative 1 over 8 pi. And now I only need to focus on that. And I find the simpler this is, the less chance I have of screwing it up, right? So it's going to be the cosine of 8 pi, take away the cosine of negative 8 pi. Okay, we're used to the cosine of 0s, pi's, and 2 pi's, but I mean, the cosine of 3, 4, and 8 pi also exist. Does anyone know what the cosine of 8 pi is? What number it is?
1.
It could be. That's one of its possible values. If it wasn't 1, I'm not saying it is or isn't, but if it wasn't 1, what would it be?
0.
That would be another possibility. Agreed? What's the third possibility? Because it could be one more thing. Could it be -1 as well?
Oh yeah,
Well,
just kidding on that 0.
now, I have got a 1 here. And let's do the cosine of -8 pi. And I have a 1 here. And 1 take away 1 is 0. So we did get 0, but it wasn't because 0 take away 0. It was because 1 take away 1. But it's still 0, agreed? And yep, that makes perfect sense. We kind of thought it would be. And we kind of were right. Okay. If you think about what a 0 might look like, I'll give you an analogy. Instead of the x-axis, can you imagine this is time and it's 0 to 24 and there's the 12 hours and there's 6 hours and we're military, there's 1800 hours, right? And up here is the temperature, right? And in this place, it's winter time and the temperature climbs up, right? Starts at freezing, right? 0 centigrade, right? Climbs up, climbs down. And then as the evening approaches, it gets colder and then for who knows whatever reason, by midnight, it's back to 0. Can you imagine that the average temperature during that entire day was 0? Even although there were some times where it was like above 2 degrees and some where it was below 2 degrees. But on average, isn't it 0? Does that kind of make sense? That 0 is a valid average value. Any questions about that? Are we cool? I'm going to give you a puzzle here. And it doesn't look particularly painful. But you've got 2 minutes to find the average value. And that's not a lot of time. Don't know if that's a help or not. There's the beginning. take Hi everyone, I just get bumped right out there. I was going to say, Bathsheba, you're frozen, but you weren't frozen, it was me. Can you all hear me? Yeah, that was weird. Okay, are we, oops, I'm not sure where the heck we are. Let me return to my screen. Are we good up to this point here? I don't know. If I bring that 7, it's not going to help much because aren't I going to end up with some more fractions in a few moments anyway, so I'm not going to bother with that. So evaluated at 27 and 125. If you add 1 to the power, you get 4/3, and if you divide by that, that's 3/4. So I get 21/4. God, this is getting ugly. 21 on the top and 4 times 98 on the bottom is 392. I should check that out in case it simplifies. 21 divided by 392. Math, fraction, enter. It does, it simplifies down to 356. Go figure. Okay, back to this fella. That's what we're going to be dealing with. So I'm going to evaluate that by finding the cube root of 125 and then raising it to the 4. Take away the cube root of 27, then raise it to power of 4. Computationally, it's better to do it that way than the other. Of course, you got your calculator here, and these numbers are nice. So that guy there is 625, and that guy there is 81. Does that look good so far? Okay, so 625, take away 81, leaves me with 544. So I have this guy, 544. I'm trying my best not to go decimal. So 3 times 544 gets me 1632 over 56. And I get 204 over 7. Do I get any agreement on that? Because I could have screwed up. I get 1 thumbs up, which is pretty good. So, okay, a little talk about what's happening tomorrow. We're going to do some weirder, if that wasn't bad enough, weirder average values. And then we're going to do puzzles. Give an example of what a puzzle would look like. If the average value of this function between here and here is equal to that number. So if you imagine you've got a function, it starts here and it finishes here, right? And it goes up and it goes down. And its average value is typically somewhere like that. Shouldn't there be a point on the curve that's got the average value? So we will get questions like, find at least one value of x where this function is actually equal to its average value. So really that'll be solve an equation. That'll be one of the puzzles. And then the others are just going to be things like applications. Suppose this function is a density function, which basically tells you how heavy something is at a given value of x. Then you could find the average density of it. That would be an example of that. So that's kind of what's going to happen tomorrow. Hopefully we'll get it finished. We will get it finished tomorrow, but hopefully we'll get it finished with enough time to start our next chapter, chapter 7. We finally get to start a new chapter. And well, we'll wait to see what that's about.